So I can start. Okay. This does a lot of, yeah. Ooh. Good morning. So my name is Guilherme. So I'm from Lisbon, although you'll see me more often at Sen than in Lisbon, but that's a detail. I want to start by trying to motivate why we should bother with jets. Okay. I'll define jets and so on and so forth, but my main aim at this point is to at least explain why I care about jets. If anyone else has to care about it, it's up to you. Okay, so over last week and this one, you have been looking at different stages of a heavy ion collision. Starting from the colliding nuclei, the collision process, everything that Mike Strickland talked about, of how to reach some form of equilibration process. You do then have what we refer to as a quark-gluon plasma, which at this point for me is just a system that has as fundamental degrees of freedom, not hadrons, but rather really quarks and gluons. This thing was created in a very violent collision. There's a huge density. There are no external forces once the collision has happened. So this thing will inevitably expand. When it expands, it cools. And we go back to the physics of hadrons. So everything hadronizes, which are represented by a very gray bubble there, because we know very little of how that actually happens. And in the end, all that experiments see are final state particles, hadrons, most time. So you probably all know the time scales written in Fermi over C of how this happens. So that's the collision process and towards thermalization process lasts about 0.1 Fermi over C. By 1 Fermi over C, we believe that such a state as a quark-gluon plasma has been formed. The cooling process takes about 10 Fermi over C. And if I translate this into seconds, so which is a more mundane unit of time, it becomes a bit shocking, right? All of this happens in about 10 to the minus 23 seconds, okay? So all this fantastic, rich physics occurs in a time scale that is absolutely tiny, okay? So there is no parallel anywhere else in physical processes of things that one tries to understand that happen in such a short time scale. Okay. So in these stages, what bothers me most or concerns me most here is things that Thomas was and will be talking about. So there are some initial conditions that hopefully we can constrain sufficiently well from other experiments, typically deep inelastic scattering experiments, or even proton nucleus experiments. For what concerns jets, actually, this is very well constrained, okay? These initial conditions. And in the end, all we have is that mass of final state particles. And it's a shame because what we want to understand is that thing that lived for about 10 Fermi over C. Okay, so this is the problem we have in heavy ion physics that probably all of you are aware of. Okay, so what do we want to do? We want to understand how the QGP functions, okay? We don't want just to assign it a temperature, we want to understand its dynamics. And one thing is to write models or theories or whatever you want to call it, like a hydrodynamic expansion, and say, okay, this is what I think happens. But we should be a bit more ambitious and we should be able to actually measure what happens, okay? So that's what brings me to how do I probe the QGP? Okay, and I always start this discussion with a cartoon, which is how do you probe anything? Okay, I mean, we only know one way, is throw things against things. It might look a bit basic, but that's the basis of all our understanding of elementary matter, is throwing things, collecting the pieces, and trying to understand how what it was before. Okay. This example is terrible because I'm colliding two complex objects, and then I'm going to collect pieces, and I want to figure out what was there in the collision, what was created, and this is a bit hopeless, and that is really true. I mean, X-particle physicists really don't make good biologists because our mind is completely biased towards throwing things against things. A collision of heavy ions is very much like a collision of two frogs. It's two rather complex objects that undergo a very complex dynamics, and we then collect pieces. Okay. So this is really not exactly the way to go, but we are still limited to throwing things against things. So what we in particle physics have as the gold standard for probing things is the DIS experiment. Okay, and in simple terms, what you do here is that one object that you scatter, not the one you want to understand, but the other one you understand very well. So we understand very well what a lepton is or electron is, and how they exchange with a charged object occurs through the exchange of a virtual photon. And this is even better because you can dial the resolution. Okay, so DIS experiment, you have control over the virtuality of that intermediate state. So you know which distance scales you are probing by the uncertainty principle, okay? Roughly 1 over that virtuality scale. Okay, so this looks like a good setup. The problem is what I mentioned before, the time life of the QGP. What I want to study lives for about 10 to the minus 23 seconds. So any idea of getting a beam of whatever to scatter off the quark-gluon plasma is absolutely hopeless. Okay, there's no synchronization technology to ever do anything like that. So if we want to mimic this setup, we have to rely on things that are produced at the same time as the QGP. So probes generated by the process itself. Okay. And hopefully we want probes where we have a dial of resolution as well, because we want to understand the QGP in its wealth of scales. So the answer to this question is what's in the corner. The answer is jets. So jets are the closest possible thing we can get to a scattering experiment using the quark-gluon plasma as our target. Okay, why jets? Why not anything else? So there's some things that are pretty unique about jets. Is this ability to dial the resolution. So jets are, I'll define what a jet is in a while. Jets are really multi-scale objects. So it's something that starts from a very high momentum scale, evolves down to a low momentum scale. So I'm probing small distances towards larger distances. Jets are not unobservable. Jets are physical objects that from which many observables can be defined. Okay, so there's a richness there. And hopefully, different observable jet properties should be sensitive to different QGP scales and properties. So this is very well done and written like that, right? I write a sentence in a slide and we are all happy. This is actually one of the most difficult things to do, is to find the exact matching between what something I measure in an experiment, which properties of the QGP is it sensitive to. We have another bonus, is that we have a very, very well-controlled benchmark. So jet physics, in the absence of a QGP, what I'll always refer to as the vacuum, so be it electron-positron collisions or even proton-proton collisions, is very well understood. It's in the realm of precision physics, so where you can calculate things to accuracies of the order of a few, if not sub% accuracy. Okay, and getting back to the beginning, this is really the only feasible close relative to a standard scattering experiment that we can think of. Okay, so back to what a jet is. Okay, so I refer to jet as a physical object. So it's a physical object that requires definition. So if I talk about a hadron, there is no definition needed. A hadron is a physical particle that has a mass that leaves a specific signature in a detector. I mean, there's no definition needed. I don't need to define what a pion is once I know what a pion is. A jet always has to be defined. And it's defined by a set of rules, okay, and parameters, what is usually referred as a jet algorithm, that tell me how to combine final state particles, okay, and when I should stop. Okay, otherwise I say, okay, my event is a jet. That's not a good definition. This, okay, this is also supplemented by something else that is a set of rules. So part of the set of rules is how I combine properties of the particles that I join together into a jet into properties of a jet. Of most common use. So there's a wealth of alternatives on how to define a jet algorithm, how to define this combination thing, which is called the recombination scheme. So my recombination scheme in all the discussion is going to be, if I have two particles that get combined together, the four momentum of the combined object is the sum of the four momenta of the constituents, which is a natural thing. It's not the only option, it's a natural thing. From the, I don't know how many jet definitions that you can think of, all that will be useful to us is the so-called generalized KT family of sequential recombination jet algorithms, okay? So these recombination jet algorithms are a big family, okay? Like animals. And there's plants, okay? And the other big family are called cone algorithms that in its most basic formulation, you just get a circle, move it around the event and see where this circle maximizes content, energy deposited in that circle. Those have many problems. So we'll talk about this, which is the things in modern use. How does this work? Is there a stick of some sort? Yes. This works in the following way. I define a distance measure, okay? So the distance between two particles, particle I and J, is given by their distance squared in rapidity and azimuthal angle. So this is a geometric distance, okay? It's an angle. And this is weighed by the transverse momentum of, so the minimum of the transverse momentum of the two particles involved, where that exponent P is an additional parameter in the algorithm, okay? I define also a distance of each particle to the beam direction. Okay? And the algorithm goes as follows. So this is heavy computational, but it's what it's done. I compute all pairwise distances and all distances to the beam, okay? I find the smallest one. Okay? If the smallest one is the distance between two particles, I recombine these two particles. Basically, I create a pseudo particle, which has the four momentum of which is the sum of the four momenta of the two. Okay, I recombine into a single particle. I remove I and J from the list, and replace it by this new particle. So I reduced my complexity of number of particles by 1. Okay, I do this and I return to 1. So I recompute everything and keep on going like this. Okay, then if the minimum is one of this distance to the beam, so not the distance between two particles, but the distance of something, which after a few iterations will all be pseudo particles that were built by recombining particles, I declare, so if this is the minimum, I declare that this object is a jet, and I remove it from the list, and I go back to 1. And I stop when there are no particles left. So I have an event, and I will cluster my event into a number of jets, okay, through this procedure. So in common use, there's 3 plus 1 options for this parameter P. So this works for any value of the parameter P. P equals 0, so there's no dependence on transverse momentum, means that particles will be clustered just based on their geometrical distance. This is the so-called Cambridge-Aachen algorithm, because there were 2 algorithms slightly different, one done in Cambridge, one done in Aachen, and then they decided to combine the algorithms and the name. So this clusters particles in an angular ordered way. I start from the smallest angular distance and build up to the biggest angular distance. Okay. Another option is to set that parameter to 1. This is the so-called KT algorithm. It's easy to understand. So if this is squared, so it's PT squared angle squared, which in collider variables, so these are collider variables, and this is the transverse momentum of the softest particle relative to the emitter, which we take to be the combination of the 2 particles. Okay, so here, what I'll get is something that is ordered in the transverse momentum of the branching that led to those 2 particles being recombined. Okay. Then a peculiar choice is to set this P value to -1. So now, -1 means that it's actually the maximum PT that I'm picking. So I start my clustering privileging pairs that have at least 1 hard particle. So this works as a seed, okay? Imagine a very busy environment. If I have a very busy environment, and if I do one of these 2 things, so here I don't care about PT, here I care about PT, but I care about PT by looking for soft things. So I start building jets from soft junk. So if I have lots of things around, I'll create these jets, find those jets, that are just collections of very, very soft particles, which in a busy experimental environment like the LHC is a problem, because if you have 20,000 particles like you have in a heavy ion collision, you start clustering things that don't have anything to do with what you want to call a jet. So this P-1 algorithm is, if you look at any LHC paper, all jets are reconstructed with the anti-KT algorithm. There's a slight complication, is that this does not fit in any mental picture of how QCD branching happens. QCD branching goes from harder particles to softer particles, along like this, goes from higher angles to smaller angles. And this is the opposite, but it doesn't matter because these are still well defined. Then there's a newish proposal, but one of your colleagues is involved in this sort of things, which is setting this parameter to 1/2. And as we'll see later, this corresponds to an inverse ordering in time. So I'm clustering things that should have happened later to the ones that should have happened earlier. So I'm giving a time picture to this, okay? Okay, so enough of, so for anyone interested in jet algorithms and how this all works, there's an extensive discussion in that seminal review. Okay, so why do I need to do this and why do I need to be very careful in doing this? What we are trying to do here is there is something that is seen in an experiment. So this is an E plus E minus experiment where everything is nice and clean. And I think any of you can see clearly 3 jets, 1, 2, 3. Okay, I don't know how well this can be seen from the distance. So for an experimentalist, a jet is intuitively a very simple object. Is just a collimated spray of hadrons. I see lots of stuff, okay, and I don't see stuff around. I call this a jet. Fine. For a theorist, what we want to calculate is I had a hard quark of gluon that fragmented, and this is what I would like to call my jet. Okay, this tree. So very energetic, breaks into 2, each one of these legs breaks into 2, so on and so forth. Okay. A jet algorithm is what makes this comparison possible. Okay. So it's a definition like that that allows me to actually compute and measure the same thing. Otherwise, it's useless, right? Otherwise, you have two communities doing different things and no one can compare anything. For the experimental side, what you need is that this method is robust and efficient, in particular. So that mess of building jets from things that did not originate from a hard pattern would not be robust, okay? Has to be computationally efficient. Otherwise, we would be still waiting for the first jet results from the LHC. So there are some algorithms that actually took something comparable to the age of the universe to compute, okay? So those are not in common use, let's say. Very important property is that all these algorithms, all these definitions have to be both infrared and collinear safe, which might sound like a big wording, just means one thing. If I add a soft particle, an infinitely soft particle, what my jets are cannot change, okay? And if I add a collinear particle, so something very close in angle, what my jet is, or what my jets in the event are, cannot change. Okay, this is the absolute requirement for things to be calculable. Okay, so there's this really correspondence between, that's what a jet algorithm is for, is that we can calculate and measure the same thing, okay? So if you like poetry, you have that a jet is a jet is a jet, a jet. In the original with the rose, but that's okay. So we talked about all these definitions, and there's a common criticism sometimes is that, oh, so if you have all these definitions, you don't know what a jet is. This is just, it's all ill-defined. It's quite the contrary. It's very well defined because you define it, okay? And you define it in a way so that it makes sense. But all these definitions give you different jets. So this is the same event. So same particles in the final state that was clustered using the KT algorithm and the anti-KT algorithm, okay? And you see that the jets are not all the same, okay? They are kind of more or less in the same places, but for instance, look at this thing and this thing, that I would get very different results. And that's life, okay? They are different. A very nice feature of this anti-KT algorithm for our experimentalist friends is that it actually gives jets that are sort of round, which makes all sorts of detector corrections much, much easier or possible. So, and this definition goes as far. There was something I should have mentioned, that there was another parameter hidden here, which is this R, which is a number I set. That if you work out how this works, it basically works as the maximum reach at which I capture a jet. because if this becomes bigger than that, my joining the particles is highly suppressed because I make my distances too big just based on that. So that works as a jet radius, which is meaningfully a radius in anti-KT algorithm that gives these circular things, not so much in the other cases with blobs, amoebas of particles. Okay. In this, to highlight the importance of these jet differences, imagine that I choose to cluster an event with anti-KT with a radius of 0.4. And then I do the same event, but I do the same algorithm, but with a radius with that parameter set to 0.2. I'll get different jets. The population is completely different. So it's not that these are just the inner core of those. By changing this parameter, I organize my event in a completely different way. You can imagine like two jets that are close by, so within a radius of 0.4, okay, that I reconstruct as one jet. And then if I set my parameter to 0.2, I'll reconstruct this as two separate jets. So it's completely different. The number of jets is different. Everything is different. Something that has become very trendy recently, and it's useful in the heavy ion context, is that, so we have this experimental necessity of doing things with the anti-KT algorithm that does not correspond trivially to a QCD history. So we want to give a history. So what we do is that we have these anti-KT jets that are robust experimentally, and then we give it a history by picking those particles that we already know are a jet and reclustering them with something, for instance, Cambridge-Shahan, which will give me angular order 3. Okay, so this is a tool that has become extremely useful in the community. So as in many other places, diversity is really a tool and a benefit rather than a problem. Okay. So in heavy ion collision, so all that I said so far is for vacuum, for PP physics, or it's general. But so how do we do it in heavy ion collisions? In heavy ion collisions, either for lack of imagination or for laziness, I don't know, or for necessity, we use the same algorithms that were invented for proton-proton physics. So typically the anti-KT algorithm. A heavy ion event is a complex thing. So here is, I mean, this picture has been shown ad nauseum, but so this is a heavy ion event where each one of these towers is proportional to the deposition of energy in that cell of the detector. You clearly see two jets here, okay? But you see all this mess, okay? What is this mess? I mean, this mess is the outcome of the quark-gluon plasma, okay? So sometimes people call it a background. No, this is the physics, okay? It's there. There's no way around. In proton-proton collisions, you get things like this, much lower, and you get things like this that have to do with the fact that in a beam crossing, many proton-proton collisions in proton-proton runs occur. Okay, that's completely different. It's you are distinguishing between different events that just happen to be recorded at the same time. This is a single collision. So there is no simultaneous collisions in heavy ions for technical reasons and for sanity. So this is really my event, my physics. But if I want to understand what these jets are, I need to subtract what would be there in the absence of jets. Okay, and this is not easy. It's not easy because this background first is large. So typically in the catchment region of a 0.4 jet in a heavy ion collision at this energy, I can't remember, this was still 276 or something like that. You have just in the catchment area of any circle of this size that I put here, I catch about 120 GeV. So this that is here is a tower of 70 GeV on top of a plateau of about 120 GeV. Okay. So what signal, what's background? It's a bit. So if I knew that that was 120 GeV everywhere, it would also be easy, right? I just cut. This fluctuates up and down, just statistically, of the order of 20 GeV. So this is really not easy. And in heavy ion collisions, what you really have, so whenever you reconstruct jets, there is always an associated background subtraction procedure. Okay, so your definition of jet has built in some specification of how you got rid of the background contamination. And this is far from trivial. But I don't care much about experiments. What I care is what has to be calculated, okay? But this discussion makes the answer to that question a bit complicated, right? What do I calculate? Actually, what is in a heavy ion jet? What do I have to subtract? What don't I have to subtract, etc. So let me just go through a few stages of things. What do I understand? So I understand sufficiently well the structure of the colliding nuclei at the energies, so at high Bjorken X, of what is needed to produce jets. So jets are produced at leading order in 2-to-2 processes. I have two incoming partons, one from each nucleus, that collide hardly and produce two outgoing partons. Okay, yes, of course, this has higher order corrections, etc. But this process here happens at an extremely high momentum scale. So the momentum transfer is enormous. It's things of the order of 100 GeV. So what this process is sensitive to space-like is something of the order of 1 over this scale, which means that it's completely oblivious to whether there is a plasma around, where there is a fan, where there is whatever. It doesn't matter, okay? So this is just like in vacuum. So this is something that in principle I can calculate to any arbitrary perturbative QCD order. Okay, this hard matrix element is something I can calculate. So this is easy. Okay. Then I see, okay, so what's going to happen in the QGP? There's two pictures here. Let me start with the simplest one, which is this one. So in the QGP, what will happen is that so there was this hard collision. There would be another parton going the other way, but there is this one that will interact with my plasma, can split. The result of the splittings can interact with the plasma, and so on and so forth. This interaction, so these are transfers for momenta and color. So first there is a diffusion in color space. So what was color connected is now connected to things of the QGP, and so on and so forth. These kicks can make the trajectory wobble, if you wish. So just calculating, and we will calculate this, okay? Just calculating this is a bit more difficult than in vacuum, okay? But there's more things. So there's coherence phenomena. So two legs that are sufficiently close together will essentially radiate as one. So I have to take that into account. And those properties of coherence, I'm not sure we'll be able to get there on these lectures. So in vacuum, it's pretty simple. The wavelength, so radiation of gluons with a wavelength that is larger than the separation of the legs that may emit it coherently, for those gluons is as if they were emitted by the mother charge or emitted coherently by the two. If they have a smaller wavelength, then they are emitted separately from each leg. So that's what's depicted here. Then all these interactions, all things, and then you'll see some novelty here, which are these funny lines. So these funny lines are just a picture talking about what happens. So if I deposit energy from my particle onto the plasma, what I'm doing is I'm hitting the QGP locally there. Okay, so in principle, the evolution of the QGP should be different from that point on. So what we know is that it's not very different because these are depositions of tiny amounts of energy. However, this creates a wake. So these depositions of energy is like a boat going in water, right? The boat going in water creates a disturbance on the fluid, and that disturbance on the fluid kind of follows my propagating object, right? So when I'm going to reconstruct a jet at the end, I'll catch these things. I'll catch what is coming from the plasma due to the excitation induced by the partons, okay, that would not be there if the jet had not been there, okay? So this is not to be subtracted. This is part of my signal because the only reason it's there, it's because jet is there. Okay. Another thing that is tricky is that things can be kicked out of what will be my reconstruction area just by interactions with the medium. So this is really a mess, okay? So this sequence of things they are separated by funny punctuation are just that this is stuff, okay? Then Andrea will be very happy to do this. Then comes the, I mean, there's always those words that you are not supposed to say, right? Or in, but it's actors never talk about Macbeth, never say the name Macbeth because it's kind of plagued that the play will go wrong and whatever. So here is hadronization, okay? So we don't understand in full detail how hadronization happens in vacuums, okay? We have very successful effective models. So like Lund string hadronization is later on now. How it is implemented in Pythia or something like cluster hadronization implemented in Herwig. The common feature of these things is that what is really important is color. You want to build colorless objects. So how things are related to each other in color makes a huge difference. So in a heavy ion collision, most, if not all, hadronization occurs after, so of things that will belong to a jet, happens outside the QGP, okay? And for a long time, people said, oh, it happens outside, has nothing to do with it have been going through the QGP. That's not true. That's not true because color correlations that were established while going through the QGP will survive because there is nothing that will alter them. So just by having gone through the QGP, you do have an effect on how your final state partons are connected in color. So how objects are going, how colorless objects are going to be built. So, and I said that Andrea would be very happy to see this because this is something that we did 10 years, 11 years ago. And I still keep this reference in this slide that I've used many times because there isn't anything else. So there's 2 papers by us, another couple of papers by another group of people, and then everyone kind of gave up. So you kind of, it's really, if you let me do away with this, I'll produce some results. Let's not talk about this. next time. Okay, so this is really tough. And now you come to what I already mentioned before, which is this, what is really a jet in heavy iron. So what I want, so there's this jet, which is the result of this branching process. There is this background that is the QGP, but then there is this disturbance on the QGP that is exaggerated here that has to do with the excitations that my partons induced on the jet. So ideally, I would like to subtract this exactly so that this would be what I calculate, this plus this. Again, very nice to write in the slide how this can be done in detail so that we know that we are measuring and calculating the same thing is not trivial. So if you are on a bad day, you would say this is probably hopeless, okay? I don't know if you recognize, oh, okay. But if you are on a good day, okay, you say that, yeah, I'm aware of all these difficulties, okay? But life goes on. So I will compute something in whatever way I decide to do it, that I can compare with some caveats to something that is measured. And from that, I understand something, or I should understand something. And that by understanding something, I'm one step further, and I might be able to remove some of the caveats that were on my thing. So it's a very constructive process that is slow, but has been working. So we know much more than what we did 10 years ago. So it's the work with what you have to eventually have more. It's a very positive outlook in the world. I don't know if anyone follows psychology, but these are the 5 stages of heavy iron phenomenology. So historical note, so this has been applied to everything, but the psychologist that actually invented this sequence, she came up with the idea while she was grading exams. So the first thing is that it was really, these were the 5 stages of grading, so that this is all fine, and all these people just do things, oh, I'll give them a few more points, I'm going to stop teaching forever, and then, oh, well, that's it. So that's how things go. Okay, so this was probably a good a long introduction to get you into the mood. So the idea is I want to go through at least part of these 5 stages. And I'm going to start with the simple building blocks, okay? Which are partonic calculations in the presence of a QGP. So I want eventually to get to calculate something that resembles that process there. Okay, doing that, and I hopefully will get to discuss how you get things that can actually be compared with data, which in my way of viewing things, it's mostly things that are done with event generators. Okay, so I want to discuss some qualitative things, and I'm going to look at the time. So we do a break at the hour, right? Okay, so this is ideal. And I want to start in vacuum, and I want to do just qualitative things for a few minutes, or probably a bit longer, which is, okay, I need to give credit. So in this initial part, I'm following some lectures, I think, by Andrew Larkowski, Jet Physics in Vacuum, or Basics of QCD in Vacuum. I can give the reference. I can then give you my written notes. So, and just start with the following observation, is that at high energies, okay, alpha S is small, okay? So the QCD coupling constant at high energies is small. And it's also approximately constant. So since this is the only scale present at high energies in QCD, this means that my my iPad wants me to do a setup. Anyway, what this means is that from this point on, if I set this to a constant, there is no scale in my theory. Okay, so by making this observation or assuming this, what I've said is that QCD is scale invariant. Okay, which you know it's wrong. Okay, the QCD coupling runs. So QCD is not scale invariant, but at high energy and in a sufficiently narrowish window of energies, which actually at high energy is very large, this number varies very little. This is a logarithmic. So if QCD is scale invariant, all things that I calculate in QCD have to be scale invariant. So let me look at the radiation of a gluon from a quark, or if you want, a quark splitting into a quark and a gluon. Let me look at this process. Okay. And I want to compute the probability of this happening, probability distribution of this happening. Okay, that you know is given by this thing squared. Okay, what I want to describe is two final particles. Okay. So what's the phase space for these two final particles? It's 2 times 4 momenta, right? I'm going to take these particles to be on shell. So I have one on shellness condition per particle. So I have 6 variables left. And then I know, or I set what's my initial momentum. So I know that the sum of these two momenta is fixed. So that's 4 conditions for the 4 components of the, so 6 minus 4 is 2. So to describe the phase space of this thing, I only need 2 variables. Is there a color? Yeah. So, so I'm going to pick those 2 variables to be the energy of the radiated gluon and the invariant mass of the pair. Okay. So invariant mass of the pair is just, I should give names to variables once in a while. Okay, this will be self-explanatory. Okay, it's the sum of the 4 momenta, all squared. Because the particles are on shell, this is just the dot product of the 4 momenta. So PQ squared and PG squared are both 0. So PQ squared, this is on shellness. Okay, and this I can write as the product of the energies, 1 minus the cosine between the quark, of the angle between the quark and the gluon. Yeah.
You said that the 4 momentum of the incoming quark is fixed.
Yeah.
So this fixes m squared, right?
No.
Why not?
Oh, fixes m squared. Yes. So okay.
So it's not an independent variable.
No, sorry, it's not. So I said something that I should re-say using different words or correct what I said. No, I have conservation of momentum. Sorry. There is no angle dependence where? So the gluon is always massless, yes, and I'm assuming that is on shell, yes.
But in that case, in the massless case,
I mean, depends on the angle through here. Okay? So what I fixed, so how do I say what I want to say properly? No, it's the sum of these things is equal to something there that I fixed. So that's fine. But this is not constant because these things are not fixed separately. I'm sorry. This is also equal to something that I know. Yes. Okay. So my invariant mass is kind of set, but this is for each invariant mass. Okay. So what you were saying is absolutely right. I fixed this quantity. So I said so if I know these four momenta, I only have two variables that this can depend on. But I'm doing this for any incoming four momenta. Okay? So, and I have this relation, then it is reflected there. Okay? So that's how the 4 degrees of freedom go away, and I only have these ones left. So this is a full characterization of the final state. For each incoming, so this is set by the incoming thing, as you said.
Yeah, but then we still need two additional variables.
No, where? For what? For whom?
But it wasn't counting because it's 8 minus 2 minus 4. So we have
2
independent.
So
It should not be fixed.
4 times 2, right? That's 4 momenta, 2 particles of my final state. Yeah? 2 on shell conditions. And final state with respect to a fixed initial state minus 4.
Yeah.
So 8 minus 2 minus 4 is equal to 2.
Yeah, but m squared is contained in the 4 which we are subtracting.
But that's what survives for the final state. This counting does not have the initial state. So specifying my initial state sets one of my variables. But I'll not set it. Will be differential in this quantity. So the counting is right.
Okay, sorry, maybe
Okay.
I should ask you.
Yeah, we can discuss it.
So, if you have two independent variables, now m squared.
Yes. Yeah, m squared is one of the two. There's but I'm not setting it straight.
There is an asymptotic integration that we don't care of.
There's an azimuthal integration that I don't care of. Yes. Okay. So, So what does my scale invariance mean in this sense? Means here? Means that if I write now my probability in terms of these variables, okay? This has to be equal to the probability where I rescale my variables. So this has to be equal to lambda EG, lambda squared m squared, d EG, d lambda EG, d lambda squared m squared. Okay. Okay, this has to be valid for any lambda larger than 0, otherwise it doesn't make sense. Okay, so this is my scale invariance, and now I can ask a question without knowing anything about QCD or anything. What's the simplest function that satisfies this? So, simplest function that satisfies this equality. So that is not difficult to work out. If I write something that is proportional to something like this, this is obviously, this obviously satisfies scale invariance, right? Okay, I'm just going to put some numbers here, which are just the strength of the coupling of the quark to the gluon. Okay, this involves that I knew something about QCD. So there is a coupling constant has to be here, the factor of pi, forget about it. And there is the Kohler-Casimir factor for a quark. So if this was a gluon from a gluon, this would be exactly the same thing, but this would be Ca. So Cf is just n squared minus 1 over 2n, so the effective Kohler charge of a gluon. Okay. That is a lambda squared, yes. Here it's a lambda squared as well, yes. So lambda is a multiplier, a scale factor. So m squared has dimensions of energy squared. So that's why I have to scale it with the square. Yeah. Okay. So I have this. So I have P e.g. m squared d.e.g. d m squared, like that. Okay, so it's also easy to see that I could multiply these by any function of the ratio of the two quantities. So e.g. squared over m squared, any function of that I could multiply here, and I would still maintain invariance. Okay, I'm going to drop those terms. So in what is called the double logarithmic approximation. So this look like logs, right? Derivatives of logs. So I'm going to drop that, and I'm just going to look at this kind of pure case with really the simplest function. And before we go and have a coffee, I just want to rewrite these in dimensionless variables. Which I'm going to pick to be the fraction of energy carried by the gluon, okay? It's a natural-ish variable. And the angle between the quark and the gluon. So this is the angle between the three momenta vectors of the quark and the gluon, which I'm going to call theta, okay? Which is given in terms of those things there by this, sorry. By that. Okay. And I can then rewrite that probability in terms of these variables. Okay, that gives me something, those same numbers, nothing happens to that ever. And if I did this right, there's a minus sign here somewhere. Okay. I want to do one more thing before we go, which is to look at these things in both the soft limit. So soft limit means that the fraction of energy carried by the gluon is very small. So if I do that, 1 z, 1 minus z goes to 1 over z. I want to look also only at small angles, so collinear splittings. So this means theta is very small, which means that d cos theta, you can do it yourselves, that this goes to d theta squared, which finally means that I can write my probability in terms of z and theta, and a rather simple form in this limit. Okay. Now, before we go, I'll just point out two things. It was not needed to do the limit for that, but it could be seen there as well, is that this is divergent. Yeah. So this is divergent when z goes to 0 and or theta goes to 0. Okay. So this cannot be a probability, right? There is no infinite probabilities. So that's where I'll pick up in. How long do we break for, Andrea?
10 minutes.
Okay, yeah,
10 minutes.
10 minutes, okay. Okay. So let me go back to where we stopped. So this observation is quite important. Okay. So I wrote something that I motivated as being a probability. It was a squared amplitude, so should be related to a probability. And now I find out that this is divergent in two limits. So to try to figure out what this means, you need a very simple physical observation. So what is a gluon that is infinitely soft? Is this distinguishable from just having the quark? And the answer is no, right? And the same thing for collinear. So if you are doing a perturbative calculation, you know that all these divergences cancel, or the Biordan perturbation theory, once you take into account virtual diagrams, right? Which is just what here is done. It's a gluon which I do not resolve. Okay, so in keeping with this language, I should reinterpret this as some sort of expectation value of the number of soft and collinear gluons. So I can reinterpret as the expectation value of number of soft collinear gluons. So there's nothing wrong with the calculation, otherwise we would be in deep trouble. And to kind of wrap this part of the discussion, I just want to write this in a very simple way. I want to write these terms here as derivatives of logs, okay? Which is just what's written there. So it's not even something very sophisticated. This I can write as okay. Okay, what this means is that my emissions populate the 1 over z, 1 over theta squared, or 1 over theta, phase space uniformly. So I can draw a picture. If this is log, let me just keep the same axis as I had here, 1 over theta squared, log 1 over z. The emissions the phase space final states is kind of uniform in this thing. Okay. So it's uniform in a logarithmic phase space, which means something else. It means that the emissions are well separated, both in angle and in fraction of energy. Okay, so there's no things in this approximation where I'm in this kind of soft collinear limit. Things are really happen far apart. Okay, so this is collinear this way. This is soft this way, and this is soft and collinear. So this apparently harmless drawing, okay, has a name. This is called a Lund diagram or a Lund plane. And it proved extremely useful in inventing observables and understanding how things work. Okay. A consequence of this, is also that if I think of successive emissions, this will be well ordered in this variable. So if I have two emissions, the second emission, according to this, should be much softer than the previous one, and also much smaller angle than the previous one. And this already gives you a hint why a jet is a jet, why I have something that is collimated rather than something that is a hedgehog, right? If this was not true, I could emit at any angle, for instance. So I would start with this, I would radiate like this, and then I would radiate like that, and I would end up with really a hedgehog. QCD doesn't work like that. It's well ordered in angle, well ordered in energy. So let me flip this around and ask what I believe is a simple question, which is how long does an emission take? Okay, we usually don't think about times, but it's a good way to proceed. So how long does an emission take? Okay, so even more schematic than before. I have one object goes into two, okay, with an angle theta here. This is my gluon, if you want, but I've given up on drawing fancy lines. It's all straight lines now. And this would be my quark or gluon, depending if this was a quark or a gluon, okay? Doesn't matter for this discussion. So how long does an emission take? The only way I know how to do this is to think what is the lifetime of this virtual state. Okay, so this is the same thing as the lifetime of the mother. So I'll use this human language of there's a mother that has two daughters, okay? And the lifetime of a virtual state, we know how to calculate it. If it's at rest, it has to be related by the uncertainty principle to the inverse of the invariant mass, right? So at rest, this time has to be something that is 1 over m, where m squared is the sum squared of the form moment of the particles. Okay, if boosted, I just have to write the correct boost for this, for a time, and this will just be the boost factor. I just have to multiply by the energy of the gluon. So, yeah, energy of the gluon divided by the invariant mass. So my lifetime, or the time it takes to have an emission, will be something that is energy of the radiated gluon. Sorry, not the radiated gluon. I'm completely sorry. The energy of the particle. There's no gluon here. It's all referring to this guy. Energy divided by invariant mass squared. Okay. So this is old, so this can go. And where is the reg? Okay. Yeah. So this is the angle between the three vectors. Yeah. Up there, yes. Yes, I am. Yes. Sorry? Which one? No, it's in energy. Here is in energy. It's a partition of the energy. So of the zeroth momentum of the form momentum. In that case, we'll use several variants of that. So good that you asked at this point. Okay, so here and m squared is p plus k squared. So I can rewrite this formation time or lifetime. So E over m squared, this will be E over p plus k squared. I assume the daughters to be real particles on shell. So this is E over 2 p dot k, which is E over 2 EQ E gluon 1 minus cos theta. Okay. If I didn't do anything wrong, which I can write. So this one carries fraction z, this one carries fraction 1 minus z. Ooh. Sorry. So 1 power of energy disappears. So I have 1 over 2 E z1 minus z 1 minus cos theta. Now I take soft and collinear. So small angle and small z. Small z, this is negligible. Small angle, this becomes 1 minus theta squared over 2. Okay, the 1 cancels with the 1, the 2 cancels with the 2. And I end up with something that is 1 over z e theta squared. Okay. Z times z is the energy of the radiated gluon. So this is 1 over the energy of the gluon theta squared. So again, here I see that the softer an emission, the longer it takes. Happens late. So it takes a long time to be resolved from the emitter. And the smallest the angle, the longer it takes. Again, it takes longer to be resolved. Okay, so if I define a transverse momentum that I'm going to write as Kpep is, remember things are on shell. In the small angle limit, this is just Eg theta. So I can write the formation time as the energy of the radiated gluon over its transverse momentum squared. Okay. So at this point, we can see, or we could see, and I'm going to leave that as an exercise for tomorrow. Can see something cute. Why that algorithm with P equals 1/2 is ordered in the inverse of the formation time of things. So I'll leave that as an exercise for our session tomorrow. We have to rewrite everything in collider variables, so it takes a bit of time. Okay, so this is all in vacuum. So in a heavy ion collision, so in heavy ion collisions, these splitting processes take place in the presence of a medium, okay? Let's call it QGP, that is dense, it's hot, and it's colored. So there's color degrees of freedom all over the place. So these propagating partons that will split interact with that background, and they exchange 2 things, or 5 things if you want. They exchange color, and they exchange for momentum. So for illustration purposes, and I'm going to justify this later on, we are going to say that the interaction with QGP of parton with QGP is simply, okay, a gain of transverse momentum. Okay. At a constant per unit length rate. Okay, so what I'm saying is that just by going through the QGP, a particle acquires a transverse momentum squared, which is proportional to the distance and to some rate that is per distance. Okay, so that Q with the hat on top is the amount of transverse momentum squared that is acquired by a particle by simply interacting with the QGP. Okay. So if I take this and I look back at my formation time, now I see that the formation time in the presence of a medium is the energy of the radiated gluon over the transverse momentum squared, but now I acquired transverse momentum, so this is Q hat L. Okay, but L and the time are essentially the same thing, right? If this propagates at the speed of light. So for L tau, what I get is that this formation time in the medium is quite a bit different from what I had in the vacuum. In particular, it tells me that softer particles have smaller formation times. So the introduction of interaction with the QGP flips things around somehow, okay? Most important thing, so before even understanding the balance between these things, this means that medium induced emissions, so this is a fancy way of saying that it's emissions that would not have occurred if there was no QGP, are ordered differently from vacuum case. But bear in mind, no one switched off there's no button that switches off vacuum physics, okay? Everything is still happening as in vacuum, but there is a new scale in the problem, which was introduced here through this. Okay, so I can do actually quite a bit just with these basic observations. Sorry, I can't hear you.
I got lost in the point here. So we are assuming that the unit rate of
Transverse momentum acquisition, yes?
is constant.
Yes, I'm assuming here that it's constant. So I have a plasma that is a brick, okay? That has constant density.
So like the next differential rate.
Yes, and I know that you do that, so, right?
No, but
No? Oh, I thought you did, okay. So there's many things I can do. So here I'm really assuming that the plasma is some medium of constant density, so that this is all well defined. And that's a good setup to at least set up analytical calculations, okay? So let me take now what would be an in-medium splitting. So something like this, and I wanted, so the picture I had before, this can interact with the QGP, but so can this, and so can this. So these things that look like photons are gluons, okay? I don't know how to do the curly ones. Okay, and to making this, I'm going to assume a medium, okay, where I can define, or I can always do this, but where it's meaningful to talk about a mean free path. So how long, how long in distance it takes to see, or the distance that separates scattering centers in the QGP, mean free path. Okay, so this means that in a distance L, the number of scattering centers that I'll encounter would be something like the distance traveled divided by this lambda n, this mean free path, okay? And I'm going to assume something very naughty, okay? Which is, I'm going to, for the purpose of our discussion, I'm going to artificially switch off vacuum physics. So, but I do that in the following way. I say that my initial parton is on shell. So if it was in vacuum, it would never radiate, right? Its lifetime would be 1/0. So I do that so that I can study or benchmark the medium effects by themselves. So I'm going to assume initial parton on shell. So in vacuum, it would never radiate. And never is the important thing here. Okay, so how do I do this? So if I was really, really naive, I would say, okay, each one of these scattering centers is going to transfer some this momentum and is going to induce a radiation, okay? So my super naive starting point is each scattering induces a radiation. Okay. What this means is that then the radiation spectrum, so spectrum, is just incoherent sum of radiations. So I know immediately how to write that. So my spectrum, I call this independent or incoherent. This would be something proportional to alpha S, which is each radiation times the number of scattering centers. Okay. So this has to be wrong. Okay, so this is wrong. Because if my mean free path is smaller than the time it takes for a radiation to occur, I'm going to encounter another scattering center before I have radiated. So I should, in that case, take into account, imagine that the formation time is something like this. I need to take the effect of these two scatterings coherently. They both contribute to a single emission, okay? So I don't know if there is a, yeah. Wrong because when formation time larger than lambda mean free path, several or more than one scattering can contribute to single emission. Okay. So not very difficult to modify our starting point calculation to take this into account. And that will do as follows. So the number of effective scatterings within a formation time is just this. Okay, it's just, there's no science here. So my emission spectrum, coherent now. I hope I'm not missing factors here. No. Is my independent one. But corrected in this way. So my, okay, by the ratio of number of effective scatterers for a single collision, then the number of scatterers. So this, just plug and play, will be something like that. Oh, but we know what the formation time is. So this we can write as like that. So this has to be a dimensional. So this is an energy here. I'll call this energy some critical energy, okay, to write this like that. So what is this energy that I defined there? So this is the characteristic or typical energy for gluons with formation time equal to the total length. Okay, and I can keep on playing. Let me just see where this ends. Yeah. I can play a bit with these scales. To do what do I want to do with these scales? For instance, so this is, if you want, it's the maximum energy that a gluon can have. So it's the gluons that were only emitted after the entire extension of the medium, L, was taken for a single emission. So I concentrate on a single emission, all the effects of the medium. If I emit earlier, then it's a reset, right? For what I'm going to do. So this is really the maximum distance, maximum energy I can radiate due to medium interactions. Another thing I can do is that I can look at an angle, okay, which will be the characteristic angle for gluons with formation time equal to L. So an angle is transverse momentum divided by energy. So in this case, it's KT omega C for this maximum one, which I can write. Okay, 1 over KT L. So this is just playing with all these relations. And in particular, I can write it as 1 over square root of Q hat L cubed. So, like a summary, so for gluons with the scale I could have introduced, yeah. Let me just do a step back. I mean, there's no science in it, but I could have introduced the typical transverse momentum here, which is Q hat tau. So for gluons with the thing, which would be square root of Q hat energy. Okay, so that this doesn't appear from nowhere. So for gluons with tau equals L, what I have is then okay, tau max, which is L, which is square root omega C over Q hat. Okay. Omega C is Q hat L squared. The maximum transverse momentum squared, which I'm going to call a saturation momentum in tribute to Thomas. No, it's really the maximum momentum, so we set it as a saturation momentum. Is Q hat L, which, as written there, is Q hat energy, energy of the gluon, which is omega C in this case, and the maximum, or the angle is 1 over Q hat L cubed, which is QS over omega C. Okay. And from these, I can then write relative quantities to these ones, to the maximum ones. It's funny, I'm always looking for a normal wiper, so I never see this. So then if I want to do this for gluons with formation time less than L, okay, and you can play with these scales. It's a good exercise as well. I'll have that tau will be L and the ratio of the energies. Transverse momentum will be this maximum transverse momentum, and again, the ratio of the energies. The angle will be this benchmark angle multiplied by the inverse ratio of the energies to the power 3/4. Okay. So here you have everything expressed in terms of relative to the maximum it can be. And so this is always smaller than that. So formation time is smaller, makes sense. Transverse momentum acquired will be smaller. And here, how does it work? So this is a number that is larger than 1. So this is larger than 1. So it means that the angles are larger. So this theta C is the minimal angle that I can have. Okay, so all these radiations occur at, so the quicker they are, the larger angle they have. Okay, it's the ones where the formation time acquired all these contributions from the medium that have the smallest angles. Okay, going back to something that I erased. No. Back to that ratio. We see here that the coherent emission, okay, leads to suppression relative to the incoherent one, right? So I radiate less. But what I radiate less are hard emissions. So if I wanted to make this big, this doesn't work out, right? So I suppressed, so this suppresses hard emissions with respect to incoherent case. Goes as 1 over square root of energy of the radiated gluon. So this suppression of emissions relative to the incoherent count, this is the Landau-Pomeranchuk-Migdal effect in QCD, which is something that probably in some quantum field theory course you saw in QED. Okay, which is a very important ingredient of the physical picture behind all formulations of pattern propagation in medium and modification of QCD in the presence of a medium. So the result of having multiple interactions with the medium triggering one coherent emission is the suppression of hard modes. Okay. In the last 2 minutes, I can still do one little thing using this formula, which is I can compute the energy loss from a parton due to radiation. So what does this mean? Is that I start with my parton, it's going to radiate with that spectrum, okay? So my energy loss is all that has been from the parton. Okay, that's very simple to do. I just integrate the the spectrum. Okay, so I have the spectrum. And I integrate the spectrum for all energies that are allowed, which is from 0 up to the maximum energy. Okay, so this is this or this. So it's not very complicated to come to the result that this is just like this. And I can plug back what this omega c meant, that this is. And this is the important thing. Energy loss due to radiative processes that are triggered, induced by the medium, goes with the square of the distance traveled. Okay. When I formulated my model, I said that the only thing is this transverse momentum transfer to the partons. So partons gain transverse momentum from the plasma. Of course, this is not all that happens. All four momenta is exchanged. So you can also imagine of something that is just momentum being lost to the plasma. We call that elastic energy loss, okay? Those processes, which I'm not going to treat in any detail, scale proportionally to the distance. So this is the dominant process for any significant traveled distance. Although it's a good plot to do, L and L squared are not that different for small values of L. It's a funny thing. No, it's so, and this is again the manifestation of the LPM effect in QCD, that this is the inverse of the energy, of the square root of the energy, that leads me to have that that thing there. So L square dependency in energy losses is something that is unusual. That's not how things usually happen. It's usually linear, okay? So this is a very peculiar property of QCD. Okay, so this is a really natural point to stop. So tomorrow, this will be a bit more hardcore, okay? I actually want to do some sort of quantum field theory calculations, more or less. So come prepared with, I don't know, a coffee or something like that. Okay, thank you.